Hello there, welcome to the Snoozy Scientist, your quiet corner of the cosmos where curiosity drifts softly into sleep and science becomes your lullaby. Before we set off on tonight's journey together, I'd love to know, where in the world are you listening from and what time is it right now? Let me know down in the comments. It always makes me smile to see how many of us are drifting off together from so many different places on this spinning blue dot. If you find yourself enjoying tonight's sleepy voyage, you can give this video a gentle like or subscribe so you never miss our next starry adventure. It helps more sleepy minds find their way here too, and I'm always grateful for that. Now, settle in, let your shoulders soften, take a slow breath. Tonight, we're going to drift alongside the stars, from the darkness they're born in, to the brilliant light they share, to the stardust they leave behind. It's a story as old as time itself, and somehow it's your story too. So close your eyes if you'd like. The stars will wait for you. They always do. And now, we begin. Long before the first star ever blinked awake, the universe was a vast, quiet ocean of darkness and possibility. It is strange to think that something so brilliant, so radiant and life-giving, could rise from something so seemingly empty. But that is one of the universe's oldest secrets. Everything begins in the dark. Everything beautiful, every sparkle of light you see tonight, was once nothing more than a drifting cloud of dust and gas suspended in an endless black sea. When you step outside on a clear night and look up, the stars feel eternal. They shimmer and glimmer, and it is easy to forget that each one was once cradled in a cosmic nursery. Long before they shone down on us, these stars were hidden, wrapped safely in blankets of gas and dust that stretched for light years across the void. This darkness is not the kind that frightens. It is a fertile, patient darkness, a womb that holds the seeds of everything to come. The universe, in its earliest days, was nothing but swirling hydrogen and helium. These were the simplest of elements, the building blocks of everything that would ever exist. They drifted quietly for millions of years, gathering and settling, sometimes colliding gently like soft waves meeting in an endless ocean. And yet, within that drifting quiet, gravity was already at work. Gravity is the silent midwife of the universe. It does not hurry. It whispers to particles, pulling them closer together, coaxing them into clumps, and when the time is right, it presses them closer still. Picture a great cloud, so massive and yet so delicate that light struggles to slip through it. Inside, little by little, certain pockets grow thicker, heavier. As more particles gather, the cloud grows denser, temperatures begin to rise. Deep in these hidden pockets, something extraordinary stirs. If you could drift inside one of these clouds, you would feel the cold of space all around you, but sense the warmth at the center where particles press close like a heartbeat, waiting to begin. This is the universal cradle. This is where stars are made. These great star-forming clouds are called nebulae. You might have seen pictures of them, the ones painted in colors that seem unreal, swirling pinks and blues, silvery wisps like cosmic silk. The Pillars of Creation is one of the most famous. It is a towering nursery of gas and dust in the Eagle Nebula, and even from thousands of light years away, it glows softly, giving us a glimpse of how stars come to life. But what you see in those photographs is only a moment frozen in time. A star's birth is far slower, more patient, like a single note that stretches across millions of years. Not every part of a nebula will form a star. Some clouds drift apart, pulled and tugged by cosmic winds until they vanish into the darkness once more. But where gravity gathers enough gas together, it begins to work its quiet magic. Particles draw closer, their collisions grow more frequent, and the temperature rises until the cloud's center glows warm. At this point, it is not yet a star, but something in between, promise, a flicker, a heartbeat not yet heard. It is humbling to imagine that from this darkness and dust, the same simple hydrogen that filled the universe after the Big Bang, every star you have ever seen has come to be. Every sunrise, every sunbeam caught in your hair, every warm afternoon beneath a bright sky, owes its light to these hidden cradles of gas and dust. Even our sun was once wrapped in a quiet nebula, gently turning under the pull of gravity, waiting for the moment when its core would grow hot enough to shine. And though we now stand on a small planet orbiting that star, the story is far from over. All around us, in the spiral arms of our galaxy and beyond, stars are being born even now. Somewhere out there, in another dark pocket of space, hydrogen is gathering, particles are pressing close, and a new light is getting ready to awaken. That is the gift of the universal cradle. It reminds us that from the quietest places, the greatest light can come. It tells us that darkness is not empty, but full of possibility. And it whispers that even in the deepest stretches of space, the story is never truly still. In this cradle of the universe, stars are born, drift, and give their light to all that will come after. It is a reminder that from the dust, from the shadows, everything beautiful can rise, and that includes you too. So for now, rest easy and remember, the stars know how to wait. They always have. Nebulae, the stellar nurseries. Out in the vast darkness of space, far beyond the warmth of our sun and the quiet of our moonlit nights, lie places where the universe gathers its breath and dreams new stars into being. These places are nebulae, the great stellar nurseries of the cosmos. Their name alone sounds like a soft whisper. Nebulae, like a sigh that drifts through the endless black. If you could visit one, you would see not just empty space, but an ocean of clouds drifting and swirling in shapes that almost defy description. These clouds are made of gas and dust, the simplest of materials, yet they hold within them the seeds of everything that will ever shine. A nebula can be unimaginably vast, stretching across dozens or even hundreds of light years. Some nebulae are so large that even the light traveling at its swiftest pace would take thousands of years to cross from one side to the other. Inside these vast clouds, tiny grains of cosmic dust float like drifting specks in a sunbeam. Hydrogen, the lightest and most abundant element in the universe, makes up most of what fills these stellar nurseries. And though they may appear empty to our eyes, these clouds contain enough material to birth thousands upon thousands of stars. When you look at images of nebulae captured by telescopes like Hubble, they appear like paintings done by a patient artist who uses only stardust and time as a brush. Swirls of red and violet, wisps of green and blue, and shadows where the dust grows thick enough to block even the brightest light behind it. These colors, while often enhanced to show their beauty, are real. They come from gases excited by the light of nearby stars, glowing gently in the darkness. The Orion Nebula, for example, is one of the brightest and closest stellar nurseries to Earth. If you have ever gazed up at Orion's sword on a clear winter night, you have seen its faint, ghostly glow with your own eyes. You are looking into a cradle of stars. Nebulae are not static. They are alive with motion, even if that motion unfolds over millions of years. Gravity is at work here, endlessly patient, always drawing particles of gas closer together. Tiny ripples in the density of the cloud grow larger with time. Where more gas collects, gravity pulls harder, gathering more material inward. Slowly, pockets within the cloud grow dense, like hidden knots within a blanket of mist. Within these dense knots, the temperatures begin to climb, though if you could somehow stand inside, you would not feel warmth the way you know it here on Earth. The warmth is at the very heart of these pockets, where atoms are packed so tightly together they begin to press and collide. These hidden knots are called protostellar cores. Imagine them as secret rooms within the nebula, sealed away by thick curtains of dust and gas. If you could peer through the dust, you would see the earliest stages of a star's life. At this stage, a star is like an infant still curled in the safety of the womb, gathering strength and warmth until it can shine on its own. Around these forming stars, jets of gas may shoot out in opposite directions, sculpting the surrounding cloud. Winds from young, energetic stars can carve out tunnels and cavities within the nebula, like secret pathways through a cosmic forest. Not every part of a nebula will become a star. Some regions drift apart, tugged away by the gentle push of nearby stars, or blown clear by the fierce winds of newly born giants. But where the balance is just right, gravity gathers enough material for fusion to begin, and a new star's light flickers on. From the darkness of the nebula, the sky gains another point of light, another sun to warm its future planets, another storyteller in the night. And when you remember that our own sun was once part of such a nursery, the thought becomes even more comforting. The earth, every ocean, every leaf, every heartbeat began as dust drifting through such a cloud. Somewhere billions of years ago, our sun's birth cry pushed away its cradle of gas, and the leftover dust gathered into the planets, the asteroids, the comets that still visit our sky, like memories of where we came from. So the next time you see an image of a nebula, or if you ever spot Orion's soft glow on a cold night, remember that you are peering into a nursery more ancient than any forest, more patient than any mountain. You are looking at the place where light is born from the quiet gathering of darkness and dust. You are seeing the universe's promise to itself, that no matter how deep the night, light will always find a way to return. These stellar nurseries remind us that from the simplest of beginnings, the most magnificent wonders can grow. And perhaps in some gentle way, they remind you too that inside every quiet shadow, something beautiful may be waiting to be born. If you could drift through the universe with no need for air or warmth, you would find that most of space feels still. It stretches around you like an endless hush, broken only by the distant glow of stars. But this silence is deceiving, because hidden within every cloud of gas and dust, an ancient force is always at work, shaping everything it touches. That quiet architect is gravity. Gravity is patient. It is never loud, never hurried. Unlike a spark that flashes in an instant or an explosion that shatters in seconds, gravity works in the deep, slow time of the cosmos. From the beginning of the universe, gravity has been the gentle hand gathering scattered things together, weaving order from chaos. It has no eyes, no voice, yet it understands exactly what must be done. Without gravity, the gas and dust floating in vast nebula would drift apart forever, scattered too thin to ever build anything lasting. But gravity whispers, and the universe listens. Imagine you are floating inside one of these nebula, surrounded by hydrogen atoms that move aimlessly, bumping into each other in the chill of space. For millions of years they drift, but gravity is always there, pulling on each one with the tiniest tug. It does not matter that the pull is weak. What matters is that it never stops pulling. Where just a few particles cluster together, they pull in others, and the growing clump gains weight in the darkness. The more mass it has, the stronger its pull becomes, and so the gathering grows. Slowly, ever so slowly, gravity spins its web. Pockets of gas that are slightly denser than their surroundings become seeds for stars. They swirl gently, drawing more hydrogen inward, packing it closer and closer until what once was thin as mist becomes thick as a storm cloud. This is how the heart of a star begins, not with fire, but with the patient folding of space by gravity's invisible hand. Inside these pockets, as gas piles up, pressure begins to build. With every new atom that falls inward, the temperature creeps higher. It is like stacking blankets on a single point until the weight creates warmth. And though the space outside remains cold, at the very center of the forming star, the heat grows fierce. This warmth is not yet the blaze of a star, but it is the sign that gravity's work is nearly done. The gas at the core has become so tightly pressed that the atoms begin to collide with a new purpose. They are ready for fusion. Fusion is the true spark of starlight, but gravity is the match that lights it. Without gravity, the hydrogen atoms would never come close enough to fuse. They would remain scattered like seeds blown into the wind. Gravity's job is to bring them together, to squeeze them so close that their very nature begins to change. In this way, gravity is not only the gatherer, but also the keeper. It holds the forming star together, balancing the outward push of the new heat with its constant inward pull. If the balance holds, the star settles into its long life, burning steady and bright for millions or billions of years. What is astonishing is that gravity works on all scales. It is the same force that keeps your feet on the ground and holds the moon in its path around Earth. It is the same force that keeps Earth circling the sun and the sun circling the center of the Milky Way. And it is the same force that brings scattered hydrogen into knots that will shine as stars. It does not rush. It does not sleep. It simply does its work, unnoticed until you look up and see the glittering proof stitched across the night sky. When you think of a star, the warmth on your skin, the golden light that filters through your window, remember that it was gravity that made it possible. Long before fusion lit its fire, gravity gathered the first whispers of hydrogen into a single point. It pressed and shaped and coaxed the cloud into something more than it was. Every star you see is a monument to gravity's quiet power. Sometimes when we stand under the stars, we feel small, and yet in some gentle way, we share this same force. You too have gravity. Your feet press into the ground because Earth holds you close. The atoms that make you were once gathered by gravity inside a star long gone, and the breath you take is made of elements forged in places where gravity once pulled with all its ancient patience. So when you gaze into the night, know that the same invisible hand that shapes galaxies and calls stars to life is always here, gently holding you in place, reminding you that you belong to the story of the stars. That is gravity's gift. It pulls us together. It turns drifting gas into blazing suns. It weaves the universe into something beautiful and enduring, and it does it all in perfect silence. Wisp, ring across the darkness, gathering the pieces of tomorrow's starlight. One gentle tug at a time, the protostar awakens. Deep inside the vast cold folds of a nebula, where the darkness feels endless and the silence stretches for light years, a tiny miracle begins to unfold. It starts so quietly that even the universe itself seems to hold its breath. Somewhere within that swirling cloud of gas and dust, gravity has done its patient work. What was once a thin fog has gathered into a dense knot of material, and in the hidden center of that knot, a new kind of light is preparing to wake. This is the birth of a protostar, a star that is not yet fully born, but no longer just a drifting cloud either. If you could slip inside that cocoon, you would find yourself surrounded by darkness so thick that not even the brightest flashlight could cut through it. Yet right at the heart of that darkness, the gas is warm, even hot, like a secret ember waiting for its flame. The moment when a protostar forms is the moment when gravity and pressure become so strong that the temperature inside the collapsing clump begins to soar. Hydrogen atoms are squeezed closer and closer together, their motion growing frantic. The heat rises to thousands, than tens of thousands of degrees. Still, it is not yet a true star. Fusion, the process that makes stars shine, has not quite begun, but the conditions are almost right. The protostar is like a baby bird in its shell, growing stronger each moment, waiting for the right time to crack through. Outside this warm heart, the surrounding gas and dust swirl like a cosmic blanket. This blanket does more than just hide the newborn star. It feeds it. Material keeps falling inward, drawn by gravity's tug. As it falls, it spirals around the protostar, forming a disk of gas and dust that spins faster and faster the closer it gets. Some of that material will be pulled into the growing star, adding to its mass and raising its temperature even higher. Some of it will stay in the disk, where millions of years later it may gather into planets, asteroids, and comets. In this way, the beginnings of entire solar systems are wrapped around the heart of a single protostar. If you could see the protostar now, you would see more than just a glowing sphere. You would see outflows, jets of gas shooting out from its poles like cosmic fountains. These jets burst through the surrounding cocoon, carrying away excess energy and helping the forming star maintain its balance. They also carve pathways through the nebula, shaping it into strange, beautiful patterns that astronomers can sometimes capture with their telescopes. The birth cry of a protostar is not loud in the way you and I know sound. Instead, it is written in these jets and winds, in the way the gas glows when struck by the streams of energy. Inside the protostar, changes are happening so slowly that they would seem frozen if we could somehow stand there and watch. But in the scale of the cosmos, they are happening with breathtaking speed. The core is gathering itself, pressing inward, growing hotter with every heartbeat of falling gas. In time, when the core temperature reaches millions of degrees, the hydrogen atoms will finally fuse. At that moment, a new star will truly shine on its own, no longer needing its dusty blanket to hide its light. But for now, the protostar sleeps inside its cocoon, drifting within the nebula that gave it life. It glows faintly in infrared light, invisible to our eyes, but clear to the sensitive eyes of space telescopes. When astronomers peer into star-forming regions, they see these hidden sparks, each one a promise that the universe's light will never run out. It is humbling to remember that even our sun was once such a spark, wrapped tight in darkness, waiting for the moment when it could open its eyes and warm the space around it. The story of a protostar is a story of becoming. It is about what happens when a simple clump of gas decides to hold itself together against the darkness. It is about patience and pressure and the quiet push of gravity that never lets go. And it is a reminder that even in places where everything seems cold and empty, warmth can grow. Light can gather itself in the quiet and prepare to break free. Tonight, as you drift into sleep, think of these hidden hearts scattered through the arms of our galaxy. Somewhere right now, a new protostar is awakening, spinning gently inside its cocoon of gas and dust. It is gathering its strength, waiting for the day when it will shine clear and bright, adding its light to the chorus of stars above your head. And maybe, just maybe, that thought can remind you that even the smallest warmth can become something that lights up the night. Birth cries, jets and winds, pure. There is something wonderfully poetic about how stars come into the world. For millions of years, a quiet cradle of gas and dust holds the forming star safe inside its dark cocoon. Gravity does its work slowly, pressing particles tighter and tighter, warming the center of the clump until it glows with the first hint of future light. But what many people do not know is that the birth of a star is not entirely silent. When a protostar grows strong enough, It finds its own way to announce its arrival. These are the birth cries of a young star, the powerful jets and stellar winds that break through the darkness, clearing a path for its first light. Imagine for a moment drifting through a cold nebula. You see vast swirls of gas, clouds that stretch for light years like a cosmic fog. Deep inside, hidden from ordinary sight, are knots of dense material where protostars are forming. In those hidden pockets, gravity's steady pull is matched by the new energy building within the star. As more gas spirals in through the surrounding disk, the star-to-be grows warmer and more massive. But there is only so much material a star can hold before it must find balance again, and so the protostar pushes back. Young stars have a remarkable way of balancing the inflow of gas with an outflow of energy. Along their poles, they blast out narrow jets, high-speed streams of gas that can travel for light years through the surrounding nebula. These jets burst through the dense clouds that once hid the star, creating long glowing trails that we can see with special telescopes. Sometimes these trails look like streaks of neon in the darkness, a signature written in gas and light. Alongside the jets come the stellar winds, streams of charged particles blown away from the young star's surface. You can think of these winds as gentle compared to the jets, but still incredibly powerful on a cosmic scale. The winds push outward in every direction, sweeping up the leftover gas and dust that surrounds the new star. Over thousands of years, these winds clear away the star's birth shroud, allowing its first light to break through and reach the wider universe. Together, jets and winds are nature's way of cleaning up the nursery. Without them, a forming star might continue to gather more and more material until it grew unstable or choked on its own birth cloud. Instead, the jets and winds act like a gentle broom, sweeping away excess gas and setting boundaries for how big the star will become. They help the star find its place in the world. When astronomers point their telescopes toward regions of active star formation, they often find these signs of newborn stars. They see long, thin jets cutting through the dark, sometimes colliding with surrounding gas and creating bright shock waves known as Herbig-Haro objects. These glowing knots of gas are like footprints that mark the journey of the jets through the nebula. They remind us that even though space may seem empty, it is alive with motion and energy. The winds and jets also do something else that is quietly miraculous. As they clear away gas and dust, they help shape what comes next. The leftover material that is not blown away may settle into a disk around the young star, where tiny grains of dust can stick together and slowly grow into pebbles, rocks, and eventually planets. In this way, the same winds that announce a star's birth also make room for future worlds to form. Every planet, every moon, every comet owes its chance to the breath of the young star that cleared the space around it. It is humbling to remember that our own sun once sent out its own birth cries. Billions of years ago, in a corner of the Milky Way, a young sun threw out its first jets and blew its winds through the cloud that had cradled it for so long. That same act allowed the swirling disk around it to settle and gather into the planets we know today, including the Earth beneath your feet. The winds that once howled through the early solar system made it possible for oceans to form, for life to grow, and for you to be here now, listening to this story as you drift toward sleep. So the next time you see a picture of a star-forming nebula or a diagram of a newborn star with its glowing jets, remember that you are looking at a moment of fierce, beautiful transformation. It is the universe's way of saying, I am here, I am alive, I am ready to shine. And just like every living thing, each star needs that moment when it pushes away the shadows and makes a place for itself in the night. These jets and winds are the first breath, the first cry, the first sign that what was once just dust and darkness has become something that will light the sky for millions or even billions of years to come. As you rest tonight, remember that somewhere out there, hidden in another nebula, a new star is crying out its arrival. With jets of gas and whispering winds, it is sweeping away its shadows, making room for light to travel across space and time. And one day, perhaps, that light will find its way to your eyes, just another starlight memory drifting through the dark, reminding you that every birth, no matter how distant, is a promise that the universe always finds a way to begin again. Finding balance, hydrostatic equilibria. It is easy to look up at the night sky and think of stars as unchanging points of light. From here on Earth, they seem so steady, so peaceful, so permanent. But inside each one of those glittering sparks, a delicate dance is taking place, a constant push and pull that keeps the star alive and glowing. This quiet struggle is called hydrostatic equilibrium, and it is one of nature's most remarkable balancing acts. To understand this balance, imagine a star as a giant sphere of gas, millions of times heavier than anything we know here on Earth. At the very heart of this sphere, the temperature and pressure are so intense that hydrogen atoms fuse together to form helium, releasing an enormous amount of energy in the process. This process, called nuclear fusion, is what makes a star shine. It is the power source that lights up the darkness and sends warmth across the emptiness of space. But fusion is not just a source of light. It is also a force that pushes outward from the star's core. Every bit of energy produced by those fusing atoms creates pressure, a steady, relentless push that tries to expand the star in every direction. If this were the only force at work, the star would keep expanding, its outer layers drifting away until the light flickered out. But the universe has a way of keeping things in check, and that is where gravity steps in. Gravity is the star's invisible anchor. It pulls every particle of gas inward, tugging all that mass toward the star's core. The more mass of the star, the stronger its gravity becomes. This inward pull works against the outward push of fusion. For a star to survive, these two forces must be perfectly matched. If the outward pressure becomes too strong, the star will expand and cool until the pressure drops back into balance. If gravity's pull becomes stronger than the outward push, the star contracts, heating the core and increasing fusion to push back again. In this way, hydrostatic equilibrium is like a cosmic heartbeat, a steady rhythm that keeps a star alive for millions or even billions of years. It is the reason a star does not collapse under its own weight or blow itself apart in an instant. Instead, it finds a balance point, a place where the push and pull are equal and opposite, creating the calm, steady light we see in our sky. Take our sun, for example. Every second, the sun fuses about 600 million tons of hydrogen into helium. The energy released by this fusion pushes outward, trying to blow the sun apart. But gravity, with its endless patience, pulls every bit of that mass back toward the core. The result is a star that remains stable, its surface gently rippling with sunspots and flares, but never drifting too far from its balanced state. This balance will continue for billions more years until the sun's hydrogen fuel begins to run low. Hydrostatic equilibrium is not just a feature of stars, it is their guardian. When a star runs out of fuel in its core, this balance breaks down. Without the outward push of fusion, gravity gains the upper hand. The star's core contracts, growing hotter and denser, while its outer layers may swell into a giant or drift away altogether. For massive stars, this imbalance can lead to spectacular supernova explosions, scattering the star's remains across the galaxy and leaving behind a dense remnant like a neutron star or black hole. In this way, hydrostatic equilibrium shapes every stage of a star's life. It is what makes stars so much more than just burning balls of gas. They are living systems, held steady by this invisible conversation between gravity and fusion. It is a fragile piece, yet it can endure for longer than any mountain or ocean on Earth, and it is this balance that allows life to exist. Without it, our sun could not shine steadily enough to warm our world and nurture every tree, every ocean wave, every heartbeat. Sometimes it helps to think of this balance like a deep breath. The inward pull is the exhale, the force that gathers and centers. The outward push is the inhale, the energy that expands and gives light. This constant exchange keeps the star alive and reminds us that even in the depths of space, the universe knows how to find harmony. So tonight, as you lie beneath the stars, remember that their calm light is not so calm on the inside. Each star is a story of balance, a reminder that even the most powerful forces can find a place to meet and hold each other steady. It is proof that the universe is capable of creating stability from chaos, light from darkness, warmth from the emptiness of space. And perhaps it can remind you that balance is not something we find just once. It is something we maintain every day, every heartbeat, every breath. Stars do not stay steady by accident. They work at it endlessly. And just like them, you too are capable of finding your own quiet center. No matter how strong the forces around you may pull, the stars above you are living proof that balance is possible, even in the vastest darkness. Ignition. Fusion begins. Inside the heart of every star, from the smallest red dwarf to the most massive blue giant, lies a quiet miracle that makes all starlight possible. This miracle is nuclear fusion, the moment when a star awakens fully, transforming from a warm, hidden protostar into a brilliant, self-sustaining light in the universe. The story of fusion is the story of how stars burn, shine, and give warmth to the worlds that orbit them. It is a story of atoms pressed so close together that they are forever changed. And imagine drifting far into space, past all the city lights, and even beyond our own sun's comforting glow. Find yourself inside a newborn star, deep in the place where pressure and temperature reach their peak. For millions of years, gravity has pulled hydrogen atoms into the star's center, squeezing them tighter and tighter, raising the temperature higher and higher until it surpasses millions of degrees. In this hidden chamber, the atoms move with incredible speed, smashing into one another with enough force to break the barrier that normally keeps them apart. Hydrogen is the simplest and lightest element in the universe. Each hydrogen atom carries a single proton in its nucleus. Under normal conditions, these protons repel one another because they share the same positive charge. But inside the core of a star, the heat and pressure are so intense that the protons no longer have a choice. They collide and stick together, forging new elements in the process. This is nuclear fusion, the act of combining lighter atoms into heavier ones. In a typical star like our Sun, 4 hydrogen nuclei fuse to create one helium nucleus. But this process is not a simple sum. When these particles combine, they do not just form helium, they also release energy, an astonishing amount of it. That energy emerges in the form of light and heat. Some of it travels outward, bouncing off particles, zigzagging its way from the core to the surface in a journey that can take thousands or even millions of years. When that energy finally escapes the star's surface, it streams across the emptiness of space as the starlight we see with our eyes and feel on our skin. Every sunrise, every warm patch of sunlight, every golden afternoon is a reminder of the fusion happening deep inside our sun, 24 hours a day, every second. Fusion is nature's ultimate power plant. It is astonishingly efficient, converting a tiny fraction of the mass of hydrogen into pure energy. This is the same principle that powers hydrogen bombs on Earth, but in the heart of a star, it unfolds not as an explosion, but as a steady, controlled burn. The balance of gravity pulling inward and fusion pushing outward is what keeps a star stable, holding it in that remarkable state called hydrostatic equilibrium. One of the most beautiful truths about fusion is that it creates more than just light and heat. It builds the elements that make everything we know. In the simplest stars, hydrogen fuses into helium, but in more massive stars, fusion goes even further. As these stars age and their cores grow hotter, they fuse helium into carbon, carbon into oxygen, and onward to elements like silicon and iron. In the hearts of the biggest stars, the periodic table itself is forged layer by layer, like a cosmic foundry. When those massive stars reach the end of their lives, they scatter these elements across the galaxy, seeding new clouds of gas and dust with the raw materials for future stars, planets, and life itself. It is humbling to think that every breath you take is possible because of fusion. The oxygen you inhale, the carbon in your bones, the calcium in your teeth, all of it was created in the hearts of ancient stars through fusion. Those stars lived their lives, shone brilliantly, and then died, releasing their enriched elements into the universe so that billions of years later you could exist. Our sun, a medium-sized star, is still in the prime of its life. It fuses about 600 million tons of hydrogen into helium every second. That number is so vast it is almost impossible to picture, yet the sun has enough hydrogen to keep burning for billions more years. When you feel the sun's warmth on your skin, you are touching a piece of that fusion, a soft echo of particles colliding deep inside a ball of gas 93 million miles away. As you lie here tonight drifting toward sleep, remember that fusion is happening right now in countless stars across the galaxy. Each point of light in the sky is a distant sun, burning through its fuel, giving light to any worlds that might circle it. Fusion is the heartbeat of the universe, a reminder that even in the darkest places, there is energy waiting to become something more. It is the promise that light will always find a way to rise from the simplest of beginnings, a few atoms pressed close by gravity's gentle, relentless hand. And that same promise lives within you too, a tiny spark of stardust glowing quietly in the night. Our familiar star, the sun's example. When you wake up in the morning and feel a warm beam of sunlight on your face, you are greeting something that began its journey deep inside the heart of an ordinary star. That star is our sun, our steady companion in the sky, our daily reminder that even the vast universe has something familiar and close. We sometimes take it for granted because it rises and sets each day without fail. But the sun is one of the most remarkable examples of how a star lives, burns, and gives life. Our sun is a middle-aged star. It is not too big, not too small. It does not blaze with the furious brightness of a giant blue star, nor does it drift quietly like a cool red dwarf. It is a yellow dwarf, a main sequence star, one of billions scattered across our galaxy. Yet, to us, it is everything. Its light nourishes every leaf and flower, warms the oceans, and provides the energy that all life on Earth depends upon. It is no exaggeration to say that every meal you have ever eaten began with the sun's gift of light. Deep inside the sun's core, the same process that powers all stars is at work: nuclear fusion. Here, hydrogen atoms are squeezed so tightly by gravity's pull that they fuse together to create helium, releasing energy in the form of light and heat. This process happens on an almost unimaginable scale. Every second, the sun fuses about 600 million tons of hydrogen into helium, and yet, the sun is so vast and so rich in hydrogen that it has been burning for around 4.5 billion years and will continue to shine for roughly another 5 billion more. But this energy does not leap straight from the core to the surface. It must first fight its way outward through the dense layers of gas that make up the sun. A single photon of light can take thousands, even millions of years to work its way from the core to the surface. Once it breaks free, it travels across the empty stretch of space at the speed of light, taking just 8 minutes to reach Earth. The warmth that touches your skin on a sunny afternoon is ancient energy that began its journey long before any human ever looked up and wondered what the sun really was. Our sun is not just a light bulb in the sky. It is a living example of balance, held steady by the same hydrostatic equilibrium that all stable stars rely on. Deep inside, the outward pressure from fusion balances perfectly with the inward pull of gravity. This balance keeps the sun from collapsing in on itself or swelling into something much larger and more unstable. It is this delicate push and pull that allows the sun to shine with the gentle constancy that life on Earth needs. Without that stability, our days and nights would not be the same. Sometimes the sun reminds us that it is still a dynamic, restless place. Solar flares and sunspots dance across its surface, bursts of energy and magnetic storms that can ripple across the solar system. These events can affect Earth in small ways, like creating beautiful auroras near the poles or disrupting satellites for a moment. They are a reminder that our sun is not just a calm sphere of light, but a churning ball of plasma, alive with energy and movement. It is humbling to know that our sun, as important as it is to us, is really just average. In the grand catalog of stars in the universe, it does not stand out. There are countless stars like it, each with the potential to warm planets, create seasons, and maybe even nurture life. When you look up at the night sky and see other stars twinkling back at you, it is comforting to know that many of them are suns too, perhaps steady and warm like ours. And yet, for all its ordinariness, our sun is special because of what it means to us. It anchors our solar system, its gravity holding Earth and the other planets in their orbits. Its light defines our days and nights, shapes our weather, and fuels the cycles of life. It connects us to the larger story of the cosmos, reminding us that we are part of something much bigger. Every drop of rain, every gust of wind, every blade of grass owes its existence to the sun's quiet burn. As you drift off to sleep tonight, imagine the sunlight that will greet you tomorrow morning. Know that it comes from fusion happening millions of miles away, in a core that has burned since before our planet had continents or oceans. The sun's light is a promise, a quiet voice whispering that some things in the universe can be constant and dependable, even in a world that changes so quickly. It is our familiar star, a small, ordinary sun doing an extraordinary thing every day, giving life to a little blue planet drifting through the dark. The main sequence life. Most stars, no matter how different they may appear to us in the sky, share one thing in common. They spend the greatest portion of their lives in a long, quiet phase called the main sequence. It is during this period that a star finds its steady rhythm, a kind of cosmic middle age where its light shines most stable and true. The main sequence is a chapter of calm in the life of a star, one that can last for millions or even billions of years, depending on how massive the star is when it begins this journey. Imagine a star that has just found its balance. After its birth, cries of jets and winds have cleared away the leftover gas and dust. After gravity and fusion have settled into their quiet dance of push and pull, the star settles onto the main sequence. From the outside, this might look like nothing more than a constant point of light, but inside, deep within its core, a magnificent process is at work every moment of every day. At the heart of every main sequence star, hydrogen atoms are being fused into helium. It is a simple reaction, but it holds the power to light up the universe. The heat and pressure in the star's core are so immense that hydrogen nuclei, which normally repel each other, are forced close enough for the strong nuclear force to bind them together. Each time, 4 hydrogen atoms merge to form one helium atom, a tiny bit of mass is lost and transformed into energy. This energy radiates outward from the core, bouncing through the dense layers of the star until it finally emerges as the light we see twinkling in the sky. For the star, this fusion is like a steady heartbeat. The energy it produces pushes outward, while gravity pulls inward, creating the balance known as hydrostatic equilibrium. As long as there is enough hydrogen in the core to keep fusion going, the star remains stable. It does not swell or collapse, it simply glows. This is why the main sequence is sometimes called the star's adulthood, a time of steady, reliable work. Our own sun is a classic example of a main sequence star. It has been burning calmly for about 4.5 billion years, fusing hydrogen into helium without interruption. Every second, it transforms about 600 million tons of hydrogen into helium, producing enough energy to light up the solar system. And yet, it has only used up a fraction of its hydrogen supply. It will remain on the main sequence for another 5 billion years or so before it begins its slow drift into old age. Not all main sequence stars live as long as the sun. The more massive a star is, the brighter and hotter it burns. But this brilliance comes at a cost. Giant blue stars, many times more massive than the sun, blaze so fiercely that they exhaust their hydrogen in just a few million years. By contrast, tiny red dwarfs, which make up the majority of stars in our galaxy, burn their hydrogen so slowly that they can remain on the main sequence for trillions of years, far longer than the universe has existed so far. These little stars are like cosmic candles that never flicker out. No matter their size, all main sequence stars share that same quiet miracle inside. They are factories of light and warmth, forging the helium that will one day become the seeds for heavier elements when the star's core grows hotter in its later stages. In their constancy, they give life a chance to grow. Planets orbit in stable paths. Climates remain steady enough for oceans, forests, and creatures to emerge and thrive. Without the calm years of the main sequence, there would be no time for the delicate experiments of life to unfold. It is comforting to think of the stars in this way. They are not just distant points of light, but companions in time. They remind us that there is beauty in consistency, that something so powerful can also be so gentle. In a universe filled with explosions, collisions, and ever-shifting galaxies, the main sequence is a stretch of cosmic peace. So when you look up at the night sky and see those countless tiny lights scattered across the darkness, know that most of them are living their main sequence lives right now. They are working quietly, fusing hydrogen into helium, sending warmth and light across the cold void. They have been doing it long before you were born and will keep doing it long after you are gone. Their calm, steady glow is a promise that even in the vast, ever-changing universe, there is a place for constancy. As you drift off to sleep tonight, Picture those main sequence stars, each one a warm, glowing hearth in the endless black. They are proof that balance is possible, that something so mighty can also be calm. And maybe, in their steady light, you will find your own place of quiet balance too. A little reminder from the stars that sometimes just being steady and true is the most extraordinary thing of all. A star's personality. Mass matters. When we look up at the night sky, it is easy to think that all stars are more or less the same. They twinkle softly above us, each one a pinprick of light in the vast darkness. Yet behind that familiar glow lies a secret truth. Not all stars live the same lives. Some will shine for trillions of years, barely changing at all, while others blaze brilliantly for a moment before fading in a spectacular finale. What decides this fate is something so simple and yet so powerful: a star's mass. A star's mass is like its personality, written in cosmic ink. It determines how hot it will burn, how bright it will shine, how long it will live, and how it will die. When a star is born inside a cloud of gas and dust, the amount of material that gravity gathers together becomes its lifelong limit. This beginning sets everything in motion. No two stars are exactly alike, but astronomers have learned to read the language of mass to predict a star's entire journey from cradle to grave. Let us begin with the smallest stars, the humble red dwarfs. These stars are the quiet introverts of the cosmos. They are small, with masses just a fraction of our sun's. Because they are so light, their cores never get hot enough to burn hydrogen quickly. Instead, they sip their fuel carefully, stretching it out over unimaginably long stretches of time. A red dwarf can burn for hundreds of billions or even trillions of years. Some of these stars formed not long after the universe began, and they are still burning steadily today. They will likely still be burning long after our sun has expanded, cooled, and vanished into memory. Red dwarfs are so faint that we cannot see them with our eyes alone, even though they are the most common type of star in the Milky Way. They drift through our galaxy like quiet candles, scattered among the brighter, showier stars that demand our attention. But do not let their faint light fool you. In their steadiness, they hold secrets about the ancient universe, about how galaxies first formed, and about the possibilities of planets circling close to a gentle, long-lived sun. Next are stars like our own sun, the middleweights of the stellar family. These stars have enough mass to burn their hydrogen at a moderate pace, not too fast and not too slow. They shine steadily for billions of years, bathing their planets in warmth and giving life plenty of time to grow and change. They live calm, bright lives on the main sequence, slowly turning hydrogen into helium. When they run out of hydrogen at their cores, they swell into red giants, shed their outer layers, and leave behind white dwarfs, small, dense remnants that will cool and fade over trillions of years. Now picture the true giants, the massive blue stars that blaze with astonishing power. These stars are the extroverts of the galaxy, burning through their fuel so quickly that their lives are measured not in billions, but in just a few million years. They shine fiercely, casting brilliant blue-white light across great distances. Their cores burn so hot that they fuse hydrogen into helium at a furious rate, and when the hydrogen runs out, they push onward, forging heavier and heavier elements in quick succession. These massive stars live fast and die young. When they reach the end of their fuel, they do not fade gently like red dwarfs or sun-like stars. Instead, they explode in supernovae, scattering newly forged elements across space and leaving behind some of the strangest objects in the universe, neutron stars, or even black holes. Their short, brilliant lives shape entire galaxies, triggering the formation of new stars and spreading the ingredients needed for planets and people to exist. In between these extremes are stars that are not quite dwarfs, not quite giants. Some are born just a bit larger than our sun and will swell into red supergiants, while others are born with just enough mass to avoid the calm retirement of a white dwarf. Every slight difference in mass can mean a dramatically different ending. The cosmos is full of these small variations, each one creating its own version of starlight and story. It is beautiful to think that something as simple as mass can decide so much. It reminds us that even in the vast cold of space, small differences matter. Mass decides whether a star will live slowly and quietly for trillions of years, or burn its way into a brilliant but fleeting blaze. It decides whether its ashes will scatter gently or be hurled across space in a final cosmic roar. Tonight, when you look up at the stars, remember that each one has its own personality, its own story, its own quiet or blazing path. Some of those tiny lights will still be shining long after our solar system is gone. Others may have already died, their light only now finishing its long journey to reach your eyes. Mass matters. It is the gentle hand that writes a star's fate, one atom at a time, in a universe where every star is unique and every light is a memory of what once was and what might yet be. Small stars, the long sleepers, out there in the vast dark sea of the universe, there exists a type of star that you will almost never see with your naked eyes. These stars do not blaze brilliantly like the great blue giants, nor do they shine with the steady glow of a sun like ours. They drift quietly through the galaxy like cosmic embers, faint but faithful, burning so slowly that they might outlast nearly everything else in the sky. These are the red dwarfs, the long sleepers of the stellar family. If you could stand among the stars and look for these tiny lights, you would need the sharpest telescope or the most patient eyes. Red dwarfs are small, sometimes less than half the mass of our sun, and often much cooler on their surfaces. Their light is not golden like our sun's, but a soft reddish glow, the color of a fire banked down to last through the night. In the cold arms of the Milky Way, these stars make up the majority of all stars we know. There are billions upon billions of them, drifting quietly between the brighter, more dramatic stars that capture our gaze. It is their very smallness that gives red dwarfs their incredible gift, time. Because they have so little mass, their gravity squeezes their cores only gently compared to larger stars. This means their nuclear fusion burns at a slow and steady pace, carefully converting hydrogen into helium bit by bit instead of in furious bursts. A massive blue giant might live only a few million years before its fuel is spent, while a sun-like star might shine for 10 billion years. But a tiny red dwarf can burn for 1 trillion years or more, its fuel lasting longer than the age of the universe itself so far. Imagine that. A single red dwarf could live through the birth and death of countless other stars. It could watch galaxies drift and merge, witness the rise and fall of planetary systems, and still glow softly through the dark. If the universe is an ancient library of starlight, red dwarfs are the stories that never quite finish, their pages turning ever so slowly. Because they are so long-lived, most red dwarfs that were born billions of years ago are still with us today. They are like ancient wanderers in the cosmic night, reminders of a time when the universe was young and filled with newborn stars. Some of these small stars may even harbor planets, circling close to their dim warmth. Astronomers wonder if these gentle, steady stars could provide a haven for life that endures far longer than our brief moment on Earth. Around such a star, a planet could orbit for billions upon billions of years, soaking up just enough light to keep its oceans liquid and its skies calm. But red dwarfs do not always stay so calm. Sometimes they surprise us. Many are known to flare up without warning, sending bursts of energy into space. These flares are powerful compared to the star's size, like sudden sparks leaping from a dying campfire. For any planets nearby, these flares can shape their atmospheres, erode their air, or perhaps stir the ingredients for life in unexpected ways. It is a reminder that even the quietest stars can have moments of fierce passion. When a red dwarf finally nears the end of its life, trillions of years from now, it will not swell into a giant or explode in a dramatic supernova. Instead, it will simply fade, burning its hydrogen so completely and efficiently that little remains to fuel a final bright goodbye. Slowly, its glow will dim until it becomes a cold, dark remnant known as a black dwarf, a ghost star, drifting silently through the endless night. No black dwarfs exist yet, because the universe is still too young for any red dwarf to have reached this stage. In that sense, the longest sleepers have yet to finish their dream. It is comforting, in a way, to know that these stars are out there. They are not the loud fireworks of the galaxy, but its steady embers, scattered like coals across a great cosmic hearth. They remind us that there is more than one way to shine. Some stars burn fiercely and quickly, others glow warm and golden for billions of years, and some choose the quiet path, a patient, unwavering flame that could outlast almost everything else. So when you look up at the night sky, remember that the brightest lights are not always the longest lasting. Somewhere out there, beyond what your eyes can see, red dwarfs drift through the darkness, holding their gentle warmth close. They are the keepers of time, the watchers of ages, the small stars with the longest dreams. And perhaps, as you drift off to sleep tonight, you can find comfort in their quiet endurance, a soft reminder that sometimes slow and steady is the strongest light of all. Medium stars, like the sun. If the universe is a vast neighborhood of stars, then the medium stars, the ones like our sun, are the quiet, dependable neighbors who watch the seasons come and go for billions of years. They are not the biggest or the brightest, but their steadiness gives life the time it needs to blossom and grow. Our sun is just one example of these medium stars, and its story is a beautiful guide to understanding how such stars live and how they change as they grow older. When a medium star is born, it spends the first part of its life in the main sequence. Here, deep within its core, hydrogen atoms fuse steadily into helium, producing light and warmth that radiate out into space. For a star like our sun, this phase lasts about 10 billion years. It is during this time that planets can form, and life, if it appears, has the chance to take root under the steady glow of its gentle star. But a star's fuel is not endless. Even the most careful spender eventually finds its reserves running low. For a medium star, the end of its main sequence life begins when the hydrogen in its core becomes scarce. Fusion slows down, and the delicate balance, that push and pull between gravity squeezing inward and fusion pushing outward, starts to shift. Gravity gains the upper hand, and the core begins to contract. As the core contracts, it grows hotter, squeezing the remaining hydrogen in the surrounding shell. This shell suddenly becomes a new furnace. Hydrogen fusion flares up in this shell, burning even more intensely than before. The extra energy pushes outward on the star's outer layers, causing them to expand. What was once a steady yellow star now swells into a red giant, a vast, bloated version of its former self. When our sun reaches this stage, Billions of years from now, it will grow so large that it may engulf Mercury and Venus. Earth, if it survives, will be scorched by the sun's expanding outer layers. But the heart of the sun, its core, will continue to change. As it contracts further, temperatures inside rise until they are hot enough for the next stage of fusion. Helium, once just a byproduct, becomes the star's new fuel. Helium fusion is more demanding than hydrogen fusion. It needs greater pressure and heat to start, but once it does, the core fuses helium atoms into carbon and oxygen. The star's energy output changes, and its outer layers respond by pulsing, swelling, and shrinking in waves that can last thousands of years. This is not a quiet time for a medium star. It becomes unstable, casting off its outer layers in shells of glowing gas. The material that once formed the star's surface drifts away into space, carried by gentle stellar winds. These drifting shells of gas become what we call planetary nebula, beautiful, delicate clouds that glow with the light of the dying core at their center. Despite the name, planetary nebula have nothing to do with planets. The name came from early astronomers who, peering through their small telescopes, thought these glowing orbs looked like distant planets. In truth, they are the star's final gift to the cosmos, a way to return its enriched material back to the galaxy. What remains at the center of this glowing shell is the star's core, now stripped of its outer layers. This small, dense remnant is called a white dwarf. No more fuel remains to fuse. There are no new reactions to push outward against gravity. But the white dwarf is supported by a strange quantum pressure that keeps it from collapsing completely. It will shine softly, cooling very slowly over billions, even trillions of years, until it becomes a cold, dark ember called a black dwarf. Our sun's story will be much the same. One day, far into the future, its calm, familiar face will change. It will puff out into a red giant, cast off its outer layers in a final, gentle sigh, and leave behind a small, glowing pearl in the darkness. That white dwarf will drift through the galaxy for longer than we can easily imagine, a tiny monument to the star that once warmed oceans, forests, and the countless lives that called its planets home. It is a comforting thought in its own quiet way. Medium stars remind us that change does not always come with violence and fire. Sometimes it comes with a slow blooming, a gentle release, and a soft goodbye that scatters the seeds for what comes next. So when you stand under the sun's warm rays, remember you are feeling the light of a star in the calm middle of its life. One day, that light will change, but its story and ours will continue drifting outward into the stars, carried on the winds of the universe's endless breath. Giant stars, the cosmic fireworks. When you look up at the night sky, your eyes are naturally drawn to the brightest stars. Some of these luminous points of light are not near at all, but unimaginably far away, their brilliance traveling across thousands of light years to reach you. These brilliant beacons are often giant stars, the showpieces of the universe, stars so massive that their short lives blaze like cosmic fireworks before ending in a spectacular finale that shapes the galaxies they live in. Unlike the small, careful red dwarfs that sip their fuel over trillions of years, or sun-like stars that burn steadily for billions, giant stars are extravagant by nature. They begin their lives with many times the mass of our sun, some with 10, 20, or even 100 times as much material packed into their cores. This extra mass means gravity squeezes them far more tightly. Their cores grow hotter, their fusion engines roar to life, and they burn through their hydrogen at a staggering pace. A giant star shines with a fierce blue-white light. It may burn thousands of times brighter than our sun, pouring out torrents of energy into the surrounding space. This energy creates strong stellar winds that blow off layers of the star's outer gas. These winds can shape the surrounding clouds into beautiful forms, clearing out cavities in nearby nebulae, and sometimes triggering the birth of new stars in the compressed gas left behind. Giant stars are creators as well as destroyers, but with all this power comes a cost. The bigger a star is, the faster it uses up its fuel. A giant star's life is measured not in billions, but in just a few million years. It is astonishing to think that a star that holds so much mass, that shines so brilliantly, should live so briefly, yet that is how the universe balances itself. These stars trade longevity for brilliance. They live fast, die young, and in doing so give the cosmos some of its most dramatic moments. Deep inside a giant star, the story is one of layer upon layer of fusion. It begins with hydrogen fusing into helium, just like in smaller stars, but when the hydrogen in the core runs out, gravity does not stop. The core contracts further, temperatures rise, and new fusion processes begin. Helium fuses into carbon, carbon into oxygen, oxygen into neon, and so on, building heavier elements like silicon and iron. The core of a massive star becomes like an onion, with each layer fusing different elements, one burning out and giving way to the next. The final act comes when the core fills with iron. Iron is the end of the line for fusion, because fusing iron does not produce energy, it consumes it. Without a way to generate outward pressure, gravity wins the final battle. The iron core collapses inward in an instant, and the outer layers crash down onto it. This catastrophic implosion rebounds in a titanic explosion called a supernova. A supernova is one of the most powerful events in the universe. For a brief moment, a single star can outshine an entire galaxy, releasing more energy than our sun will in its entire lifetime. The blast hurls the star's outer layers into space, scattering newly forged heavy elements, gold, silver, uranium, and more, into the cosmic winds. These elements will drift for eons, joining clouds of gas and dust that will someday form new stars, planets, and perhaps life itself. In this way, giant stars seed the universe with the raw materials for everything we see around us. What remains at the center depends on the mass of the original star. Some will leave behind a neutron star, an object so dense that a teaspoon of its material would weigh more than a mountain. Others, the very largest, will collapse even further into a black hole, a place where gravity is so strong that not even light can escape. These remnants are the echoes of a giant star's brilliance, reminders that nothing in the universe is truly lost, only transformed. It is humbling to stand under a night sky and realize that every heavy atom in your body was once born in the heart of a massive star that lived and died billions of years ago. The calcium in your bones, the iron in your blood, the gold in a wedding ring, all of it was forged in these cosmic fireworks. Giant stars burn themselves away so that the universe can build new worlds and new lives. So the next time you see a bright blue star shimmering far above, remember what you were looking at. You were seeing a star in its prime, burning hotter and faster than our sun could ever dream. It is a fleeting flame, a burst of brilliance that will light the universe for only a heartbeat in cosmic time. And when it goes, it will not fade quietly. It will go out with a roar, a final shout of light and energy that will echo through the ages, making sure that its short, spectacular life was not lived in vain. And as you drift toward sleep tonight, let that be a reminder that sometimes the brightest lights are not meant to last forever, but what they leave behind can shine on in countless ways, scattered like stardust across the endless night. Red giants and supergiants. Somewhere in the story of almost every star, there comes a moment when things begin to change. A star that has lived for millions or billions of years in quiet balance starts to feel the slow shift inside its core. Its fuel is running low. Its steady life on the main sequence is nearing its end. What happens next is a transformation so magnificent that entire constellations can be shaped by its light. This is the swelling of a star into a red giant, or for the truly massive, a red supergiant, a final breathtaking bloom before the end. Let us begin with stars like our Sun, medium-sized, steady burners. For billions of years, a star like this spends its life turning hydrogen into helium at its core. But eventually, the core's hydrogen is used up. The fusion that once pushed outward against gravity slows down. The balance that kept the star stable begins to tilt. Gravity pulls inward, squeezing the core tighter, raising its temperature higher than ever before. Surrounding the shrinking core is a shell of hydrogen that still has plenty of fuel. As the core contracts, this shell heats up enough to ignite hydrogen fusion again, but this time it happens in a thin layer wrapped around the exhausted core. This shell burns more fiercely than the old core fusion ever did, pouring out extra energy that pushes the outer layers of the star outward. The result is dramatic. The star swells. Its surface drifts away from the searing heat within, cooling and glowing with a reddish hue. The once compact star becomes a red giant, hundreds of times larger than its original size. From afar, these swollen stars look calm, their light warm and steady in the night sky. But up close, they are restless giants. The outer layers are now so distended and fragile that they drift and ripple like a vast cosmic atmosphere. Huge bubbles of gas rise and fall across their surface. Winds blow material away, sending streams of gas drifting into space. This shedding of layers is gentle compared to the spectacular deaths of the biggest stars, but it is no less important. The gas that floats away will someday join new clouds of star-forming material, helping to build the next generation of stars and planets. Inside the red giant, the core keeps changing. As it shrinks, the temperature eventually becomes hot enough for helium fusion to begin. Helium atoms fuse into carbon and oxygen, producing more energy to keep the outer layers puffed up. For a time, the star finds a new balance. It may pulse gently, expanding and contracting as the delicate tug-of-war between gravity and fusion shifts back and forth. These pulses can create beautiful rings and shells of gas that drift away and glow softly when illuminated by the dying star's light. For massive stars, the story is even more dramatic. These stars do not become just red giants, they become red supergiants. They start their lives many times heavier than our sun and burn through their hydrogen much faster. When their cores run out of hydrogen, they too swell, but on a scale that makes our sun's future expansion look tiny. A red supergiant can be so enormous that if it replaced our sun, its surface would reach all the way out to the orbit of Jupiter. Betelgeuse, one of the bright stars in Orion's shoulder, is a famous red supergiant. Its ruddy glow is a sign that it is near the end of its life. Inside a red supergiant, the core fuses not just helium, but heavier elements too, building up layers like the rings of an onion. Each shell fuses different elements: helium, carbon, oxygen, and beyond. The core grows denser and hotter, while the outer layers swell and drift ever further into space. Powerful stellar winds carry huge amounts of material away. This is not just waste, it is the raw material for the universe's future. The carbon and oxygen that will one day be part of planets, plants, and people are born in these moments. Eventually, a medium star like our Sun will shed its outer layers completely, leaving behind a beautiful glowing shell called a planetary nebula. At the center, the core remains as a white dwarf, cooling slowly over billions of years. A red supergiant's ending is more violent. Its core becomes too full of iron to fuse further. Gravity takes over completely, and in an instant, the core collapses. This triggers a supernova, blasting the outer layers into space with unimaginable force. Whether a gentle drifting away or a final thunderous explosion, the swelling of a star into a giant is one of the universe's most beautiful transformations. It reminds us that endings are not always about silence and darkness. Sometimes they are about release, a star sharing its riches with the cosmos before it goes. The next time you see the soft red glow of Betelgeuse or any giant star hanging in the night sky, know that you are looking at a story in its final chapters. Its light is a whisper from a star that has grown old and vast, a reminder that even in the universe's grandest farewells, there is a promise of new beginnings hidden in the drifting clouds of stardust left behind. Shedding layers, planetary nebula. Imagine for a moment that you are drifting through space, far from the busy chatter of Earth, floating in a quiet corner of the galaxy. Ahead of you appears what looks like a delicate glowing blossom, suspended in the blackness, a swirl of colors, a luminous bubble, like a flower unfolding its petals in slow motion. This is a planetary nebula, one of the universe's most beautiful and gentle farewells. It is the final breath of a medium star, a story of letting go that turns starlight into cosmic art. Despite their name, planetary nebulae have nothing to do with planets. Early astronomers, peering through small telescopes, saw these softly glowing orbs and thought they looked like distant planets drifting through space. The name stuck, but what you see when you look at a planetary nebula is not a planet at all. It is a star's outer shell, cast off and lit up by the hot glowing core left behind. The journey to this glowing flower begins when a star like our Sun exhausts the hydrogen in its core. Fusion slows down and gravity takes over, pulling the core inward and squeezing it tight. But all that pressure ignites new reactions in the surrounding shell of hydrogen, which burns even hotter than before. This sudden surge of energy pushes the star's outer layers outward. The star swells into a red giant, growing larger and cooler on its surface, but fiercely alive inside. During this time, the star becomes unstable. The balance between the inward pull of gravity and the outward push of fusion wavers like a flickering candle flame. Giant bubbles of gas form and rise through the star's outer layers. These layers are so distended, so puffed up, that they are only loosely held by the star's gravity. With each pulse, each burp of energy from the core, material drifts away into space. This shedding of layers does not happen all at once. It can take thousands of years for a medium star to slowly peel itself apart. The gas drifts outward in shells, each one moving away from the shrinking core at its center. As more material is lost, the star's once bright surface grows thinner and thinner until what remains is a tiny hot core surrounded by a cocoon of gas. Here is where the magic happens. That exposed core, now a white dwarf, is incredibly hot. Its fierce ultraviolet light floods into the drifting shells of gas, energizing the atoms and making them glow. The gas that was once hidden inside a living star now shines softly across the darkness of space. The result is a planetary nebula, a cosmic flower blooming in colors of red, green, blue, and violet. Each color comes from different gases. Hydrogen glows red, Oxygen gives off greenish blue. Nitrogen and other elements add their own shades to the delicate dance. Some planetary nebulae are simple circles, like halos around a ghost star. Others form intricate patterns, rings within rings, loops and filaments, spirals and butterfly shapes. These shapes are shaped by gentle breezes of stellar wind, by the star's rotation, by magnetic fields, and sometimes by the gravitational tug of a nearby companion star. The Helix Nebula, the Ring Nebula, and the Cat's Eye Nebula are some of the best known, each one a unique signature left behind by a star saying its long goodbye. It is humbling to realize that our sun will one day do this too. In about 5 billion years, when its hydrogen is nearly gone, our familiar yellow sun will swell into a red giant, shedding its outer layers into space. Earth may not survive that transformation, but the dust and gas that once warmed our world will drift out to join the vast interstellar medium. There, our sun's breath will mix with other clouds of gas, perhaps someday helping to form new stars, new planets, and maybe even new life. The white dwarf that remains at the center of a planetary nebula is like a glowing ember left after a fire. It no longer has the fuel to burn bright like before, but it will shine softly for billions of years, slowly cooling and dimming until it becomes a cold, dark remnant called a black dwarf. No black dwarfs exist yet, because the universe is still too young for any to have formed. Somewhere in that distant future, the final echo of a once brilliant star will slip into the darkness, its last light joining the quiet hum of the cosmos. As you drift toward sleep tonight, imagine those glowing flowers scattered across the sky, petals of gas drifting gently away from a star that has given all it could. These cosmic blooms remind us that letting go can be beautiful, that even endings can light up the dark, and that what we release into the world may carry seeds for something new. So the next time you see an image of a planetary nebula, a swirl of colors painted against the black, remember that you are looking at a star's final gift to the universe, a whisper of light and color that will drift on long after its maker is gone. White dwarfs, stars' gentle embers. If you have ever watched the last coals of a campfire glow in the darkness, you have seen a small reflection of what happens to many stars at the end of their long, luminous lives. Not all stars go out in a blaze of cosmic fireworks. Some finish their journey as gentle embers, glowing softly for billions of years before they finally fade into the quiet of the universe. These are white dwarfs, the dense, enduring hearts of stars that were once like our sun. Imagine a star like our sun. For billions of years, it burns with steady light, fusing hydrogen into helium in its core, balancing the inward pull of gravity with the outward push of fusion. But eventually, that balance can no longer hold. The star runs low on hydrogen, its core contracts, and its outer layers swell outward, transforming it into a red giant. In this swollen phase, the star sheds its outer gas in drifting layers, which float away and form a glowing halo, the beautiful planetary nebula we talked about before. Left behind at the center is the core, a small, dense remnant made mostly of carbon and oxygen, which can no longer fuse into heavier elements. It does not have the mass to squeeze its atoms any tighter. Instead, the core becomes what we call a white dwarf. It is tiny by cosmic standards, often no larger than Earth, yet it holds about half the mass of the sun packed inside. Imagine squeezing something 1,000,000 times the size of our planet into a space no bigger than our world. This is the quiet marvel of a white dwarf. What keeps a white dwarf from collapsing further is not the same force that held its parent star together. In the core of a living star, the battle was between gravity and the energy from fusion. But in a white dwarf, fusion is gone. What remains is a strange quantum pressure called electron degeneracy pressure. This delicate quantum rule says that the electrons inside cannot all occupy the same energy level. They push back, creating just enough resistance to hold the star's structure in place. It is like a cosmic balancing act at the smallest scale. A newly formed white dwarf is incredibly hot, sometimes with surface temperatures exceeding 100,000 degrees. But without fusion to create new energy, it has no fuel left to keep burning, so it slowly cools. Over billions of years, a white dwarf radiates its stored heat into the surrounding space, shining like a soft ember at the end of a great fire. It may continue to glow for longer than the current age of the universe. In fact, no white dwarf has yet cooled completely because the universe simply has not existed long enough for that final chapter to arrive. When you picture a white dwarf in your mind, imagine it floating where its parent star once lived, surrounded by the vast darkness of space. No longer does it send strong solar winds or flares. No planets orbit close enough to bask in its warmth. If any worlds survive the red giant phase, they drift far from this tiny dim star, cold and lifeless under its pale light. And yet, this tiny star remnant remains, a silent witness to the ages. Our sun will become a white dwarf too. One day, after its red giant phase and the gentle release of its outer layers, the sun's core will settle into its final form. For a time, it will shine brilliantly at the heart of a colorful planetary nebula. Then, as the nebula fades into the dark, the white dwarf will stand alone. It will spend the next tens of billions of years slowly losing its warmth. Long after Earth has become dust and the planets have drifted away, our sun's tiny ember will still glow, a tiny reminder that nothing in the universe truly disappears overnight. Eventually, in a time so distant we can barely grasp it, even these white dwarfs will grow cold and dark, becoming what astronomers call black dwarfs, invisible relics that mark where stars once lived. But the universe is not old enough for any star to have reached that stage yet. For now, all white dwarfs still shine somewhere out there, their light mingling with the glow of younger stars and drifting nebula. When you lie under the stars, it is easy to feel small, but remember that you too are made of the elements forged in these ancient fires. Some of the atoms in your bones and breath were formed in the cores of stars that became white dwarfs long ago. You are made of stardust that once glowed like an ember and drifted through space until it found its way to this little blue world. So tonight, if you need comfort, think of these tiny, persistent stars. Think of the quiet courage of a white dwarf, a star's last light shining softly through the endless dark. It is a promise that even when the brightest fires burn out, something beautiful can remain, glowing gently, carrying a memory of what once was. Supernova, the final act of giants. Not all stars drift quietly into the dark like gentle embers. Some stars, the true giants of the cosmic stage, save their most dramatic performance for last. They live fast and bright, burning through their fuel in just a few million years, and when the end comes, they do not fade. They erupt in a final breathtaking explosion called a supernova, one of the most powerful and beautiful events the universe has to offer. Imagine a star many times the mass of our sun, burning so fiercely that its core is like a cauldron of ceaseless fusion. As the giant star ages, it does not stop at turning hydrogen into helium. Its powerful gravity squeezes its core so tightly that even when the hydrogen is gone, fusion does not end. Helium fuses into carbon and oxygen. Carbon fuses into neon and magnesium. Shell by shell, layer by layer, the core becomes a nested puzzle of elements, each burning hotter and faster than the one before. This is the star's last attempt to hold off gravity's relentless pull, but inside this giant, a limit awaits. The final element that the core can fuse into is iron, and here the story takes a turn. Fusing iron does not release energy. Instead, it costs energy. The delicate balance that has kept the star steady for millions of years begins to unravel. The iron core grows heavier with every passing day, pressing down harder and harder under its own weight. Then, one day, the core can take no more. Its mass reaches a point where even the quantum pressure that held it up can no longer resist gravity's pull. In a fraction of a second, the iron core collapses in on itself, crushing atoms and electrons into an unimaginably dense ball. This collapse triggers a sudden rebound, an outward shock wave that races through the layers above. What happens next is nothing less than a cosmic thunderclap. The outer layers of the star, now unsupported, slam inward, meet the shock wave, and are hurled back into space in a titanic explosion. This is the supernova, a brief flash that can outshine an entire galaxy. For a few days or weeks, the light from this dying star can be seen across millions of light years, its brilliance a final message echoing through the universe. Yet a supernova is more than just a bright farewell. It is also a forge. Inside this roaring blast, temperatures soar so high that new elements form in the fire. Gold, silver, uranium, and countless other heavy elements are born in this violent moment. They are scattered like seeds into the interstellar medium, joining the gas and dust that will one day form new stars, planets, and perhaps even life. It is humbling to realize that the iron in your blood, the calcium in your bones, and the gold in a wedding band all began in the heart of a dying giant star that exploded long before our solar system existed. What remains at the heart of the supernova depends on the star's original mass. For some, the collapsing core crushes itself so tightly that the protons and electrons combine to form neutrons, leaving behind a neutron star. Imagine something as massive as our sun packed into a sphere no bigger than a city. These neutron stars are cosmic marvels. They spin rapidly, beam out intense pulses of radiation, and have gravitational fields so strong that they warp the space around them. In the case of the most massive stars, even neutron pressure is not enough. The collapsing core falls inward endlessly, creating a black hole, a region of space where gravity is so strong that nothing, not even light, can escape. These black holes become the ultimate tombstones of giant stars, hidden yet powerful, shaping the space around them for millions of years to come. Astronomers have been able to watch these explosions across the universe. Some of the earliest supernovae ever seen were recorded by ancient observers who did not know what they were looking at. In the year 1054, a star exploded in what we now call the Crab Nebula. Chinese astronomers wrote about a new light in the sky, so bright that it was visible during the day for weeks. Even now, almost 1,000 years later, the ghostly remains of that explosion still drift through space, a beautiful tangle of gas and dust glowing from the energy of what was once a mighty star. So when you look at the night sky and imagine the lives of stars, remember that not all will dim quietly into the dark. Some will roar, scattering their light and elements across space in a final fiery act that shapes the universe itself. Supernovae remind us that sometimes the greatest beauty lies not in gentle fading, but in the brilliance of a last spectacular gift, a cosmic blaze that makes sure nothing is truly lost, only transformed into the building blocks for what comes next. And somewhere, Out in the night, the ashes of ancient supernovae drift through the void, waiting for their chance to become something new, a reminder that in the universe, endings are never really the end. Neutron stars, the cosmic pulsars. When a massive star ends its life in a supernova, most of its material is blown out into space in a spectacular wave of light and heavy elements. But deep at the center of that explosion, something strange and beautiful can remain behind. If the star is massive enough to collapse under its own gravity, but not quite massive enough to become a black hole, it leaves behind one of the universe's most extraordinary relics, a neutron star. Imagine a single star, once millions of miles wide, collapsing in the blink of an eye until its core is no bigger than a city. Now picture all the mass of our sun squeezed into this space, so dense that a teaspoon of its material would weigh more than a mountain here on Earth. This is what a neutron star is, a cosmic paradox, so small, yet so heavy, so dark, and yet sometimes so bright. To understand why neutron stars are so special, we must return to the supernova. When the iron core of a massive star collapses, the pressures are so extreme that electrons and protons are forced together, combining to form neutrons. What is left is a sphere made almost entirely of neutrons, packed together so tightly that they resist further collapse only because of neutron degeneracy pressure, a quantum rule that, like a white dwarf's electron pressure, holds the structure in place against gravity's crush. But this tiny sphere does not just sit there, it spins, and because of how physics works, the core's rotation speeds up as it shrinks. A collapsing figure skater spins faster when pulling in their arms, and the same idea applies here. Many neutron stars spin dozens or even hundreds of times every second, creating one of the universe's most hypnotic light shows. Some neutron stars beam out jets of electromagnetic radiation from their magnetic poles. These beams sweep through space like the beam of a lighthouse. If Earth happens to lie in the path of these cosmic beams, we detect regular pulses of radio waves, X-rays, or visible light every time the beam swings past us. That is why we call these spinning neutron stars pulsars, because they appear to pulse with an almost perfect rhythm. The first pulsar was discovered in 1967 by a young astronomer named Jocelyn Bell Burnell. She noticed a series of steady repeating radio signals that clicked with such precision that she and her team half-jokingly called it LGM, short for Little Green Men, before realizing it was not aliens, but a neutron star, spinning and beaming its heartbeat across the galaxy. What makes pulsars even more incredible is their stability. Some pulsars keep time more precisely than the best atomic clocks humans have ever built. They spin steadily for millions of years, slowing down only gradually as they lose energy. And yet, these steady cosmic metronomes can sometimes hiccup. They suddenly speed up or slow down, a reminder that inside these dense cores, matter is so strange that its behavior can bend our understanding of physics. Neutron stars come in many varieties. Some pulsars orbit with companion stars, stealing material that creates spectacular outbursts of X-rays. Others wander alone through the galaxy, remnants of supernovae long past, drifting like cosmic ghosts with their powerful magnetic fields stretching for miles around them. One of the most astonishing facts about neutron stars is their magnetic power. A neutron star's magnetic field can be 1 trillion times stronger than Earth's. Some neutron stars, called magnetars, take this to an extreme. These magnetic titans occasionally release enormous flares of energy, enough to scramble satellites and even affect Earth's atmosphere if one were ever close enough. Thankfully, none are near enough to trouble us, but they are out there, a testament to the universe's boundless variety. It is humbling to think that these tiny dense objects are the leftover hearts of once mighty stars. They show us that even in destruction, there is beauty and order, a pulse that can travel across thousands of light years to reach our radio telescopes here on Earth. Long after the star's light has vanished, its heartbeat remains, like a note ringing out long after the bell has been struck. So when you hear the word pulsar, picture a tiny sphere no bigger than a city, spinning hundreds of times every second, sending out beams of energy that sweep across the galaxy like the arms of a cosmic lighthouse. Somewhere out there tonight, these neutron stars are ticking away, keeping time not just for themselves, but for the universe, marking the echoes of ancient supernovae with every spin. As you drift into sleep, think of these quiet cosmic guardians. They are reminders that even after great explosions and endings, a steady rhythm can continue. A heartbeat remains in the dark, pulsing through the endless night, telling a story of what once was and what still is, the quiet strength that endures when the bright light has gone out. In a universe of chaos and change, even a tiny spinning star can shine with purpose, sweeping its beacon across time and space to say, I am still here. Black holes, gravity's abyss. There is a place in the universe where gravity grows so powerful that even light cannot find its way out. A place where the known laws of physics bend and stretch like a canvas pulled too tight. These places are black holes, the darkest and most mysterious children of dying stars. When we look up at the night sky, we cannot see them with our eyes alone, yet we know they are there, silent sentinels marking where a giant once burned. A stellar black hole begins its story much like a neutron star does. It is born from the collapse of a massive star that has spent its fuel and lost its fight to keep gravity at bay. Imagine a giant star burning bright for millions of years, forging heavier and heavier elements in its core, building the layers of an onion that one day will fall apart. The star's final act is a supernova, a brilliant explosion that tears away its outer layers, leaving behind a heavy core with nowhere left to go. If that leftover core is massive enough, it does not stop collapsing at the stage of a neutron star. Gravity presses it further, beyond the point where neutrons can hold it up. The core crushes itself into something so dense that it forms what we call a singularity, a point of infinite density at the very heart of the black hole. Around this point exists the event horizon, the invisible boundary that marks the point of no return. Anything that crosses this threshold, a particle of light, a drifting comet, even the remains of a companion star, is trapped forever, spiraling inward toward that hidden center. Black holes are nature's great paradox. They have no surface you could stand on, no solid shell to touch. They are not holes in the traditional sense, but regions of space where gravity has carved out an abyss so deep that nothing can climb back out once it falls in. Light, which normally travels at the ultimate speed limit of the universe, slows and curves around a black hole until it either escapes or vanishes past the event horizon. For many people, the idea of black holes is unsettling. How can something be so powerful that even light, the fastest traveler we know, cannot escape? Yet, in the vast web of the cosmos, black holes are not monsters to fear, but essential actors in the dance of galaxies. They pull in gas and dust, shaping the birthplaces of new stars. They keep entire star clusters bound together with their gravity. They recycle matter and energy in ways that help galaxies grow. Astronomers detect stellar black holes not by seeing them directly, but by watching how they affect what surrounds them. Some black holes feed on nearby stars, pulling streams of gas into a spinning disk called an accretion disk. This swirling gas heats up to incredible temperatures, glowing brightly in X-rays before it crosses the event horizon and vanishes forever. When a black hole feeds like this, it can outshine everything around it, giving away its secret presence to telescopes here on Earth. Sometimes a black hole will have a companion star. As the two orbit each other, the black hole's gravity steals gas from the star, creating spectacular outbursts of energy. These cosmic vampires have inspired stories and myths, but in reality, they are simply gravity at its most extreme, reminding us that the universe is a place where opposites coexist. Light and darkness, creation and collapse, beginnings and endings. It is even more astonishing to realize that black holes are not rare. Our galaxy, the Milky Way, is filled with them. Some drift alone in the darkness, the remains of massive stars long gone. Others may lurk in star clusters, hidden until something wanders too close. And at the center of our galaxy sits a supermassive black hole, millions of times the mass of our Sun, a reminder that these gravitational giants exist at every scale. Despite their reputation, black holes do not endlessly devour everything in sight. If our Sun were magically replaced by a black hole of the same mass, Earth would continue orbiting just as it does now, only without the Sun's light and warmth. A black hole's gravity only traps what strays too close. From a distance, its pull is no different from any other object of the same mass. When you think of black holes, do not picture only darkness. Picture a story of balance, the final chapter of a star that burned so fiercely it could not hold itself together. Picture a region of space where time and light bend, where the very fabric of the universe folds in on itself. These are not just voids, they are memories of what once was, reminders that even the most brilliant fires can leave behind a shadow that shapes everything around it. So tonight, if you feel small in the face of such mysteries, remember that even in the places where light cannot escape, the story continues. Somewhere beyond the event horizon, gravity holds the echoes of a star's life, hidden away like a secret yet to be told. And out here in the quiet of your room, you can drift to sleep knowing that even gravity's abyss is part of the same vast universe that gave us the stars, the light, and the dreams we carry as we look up into the night. The stardust cycle? When we look up at the stars, we often see them as tiny lights fixed in the darkness, each one distant and eternal. But the truth is far more beautiful and far more comforting. Stars do not last forever. They are born, they live, they grow old, and when they die, they do not simply vanish into nothingness. They give back. They become the seeds for something new. This endless giving and becoming is what astronomers lovingly call the stardust cycle, the quiet truth that everything you see, and even you yourself, are part of the star's long, patient story of renewal. Imagine a giant star at the end of its life. Its core has burned through all its fuel, layer after layer, forging heavier elements like carbon, oxygen, and iron. When it finally collapses and explodes in a supernova, its ashes are not wasted. That explosion flings the star's enriched guts across space. Hydrogen and helium mix with carbon, nitrogen, gold, and countless other elements, scattering them like pollen drifting on the wind. These tiny grains and particles drift through the galaxy, joining vast clouds of gas and dust. These clouds are more than empty space. They are nurseries waiting for their chance. In the cold regions of these clouds, tiny grains begin to cling together. Dust gathers into pebbles. Pebbles gather into larger clumps. Gravity does its quiet work, drawing more and more material into denser knots. Over millions of years, These knots may become so heavy that they collapse inward, heating up until they ignite. And so, from the remains of one star, a new star is born. It is humbling to realize how much of this happens out of our sight. If you could drift through the spiral arms of the Milky Way, you would see enormous nebulae glowing faintly in the light of young stars, just beginning to shine. Some of these regions are the direct result of past supernovae. The Orion Nebula, for example, glows with the energy of newborn stars that formed from material left behind by older generations. The cycle is everywhere, woven into every corner of the sky. But the story does not stop with stars alone. Around these new stars, leftover dust and gas swirl into spinning disks. Within these disks, grains collide and stick, slowly building up into rocks, then boulders, then baby planets called planetesimals. Over millions of years, some of these will gather enough mass to become fully fledged planets. Others remain as asteroids and comets, drifting remnants of that creative chaos. On some lucky worlds, the story goes further. Water may form in the cold reaches of these young solar systems, carried by comets, or formed from hydrogen and oxygen in the swirling dust. The heavier elements, carbon and nitrogen, become the building blocks of molecules that can link and twist into the complicated chains we call organic matter. Given time and the right conditions, these ingredients may stir into something more. On at least one small blue planet orbiting an ordinary yellow star, that stardust became forests and oceans, creatures that swim and fly and dream. It became you and me. When you hold out your hand and see the sunlight touch your skin, you are feeling the warmth of hydrogen atoms fusing inside a star. When you take a breath, you draw in nitrogen and oxygen forged in ancient stars that died long before our Earth existed. Even the iron in your blood, carrying life through your veins, was born in the heart of a massive star that ended its life in a titanic explosion. In this way, you are not just a passenger in the universe. You are living proof that the stardust cycle works. This cycle will continue long after we are gone. The sun will one day swell into a red giant, shedding its outer layers into a glowing planetary nebula. Its ashes will join the galaxy's clouds of gas and dust, mixing with the remnants of countless other stars. From that cosmic soup, new stars will form, new planets will take shape. Perhaps far in the future, other beings will look up at their sky and wonder where their stardust came from. And maybe, in some small way, it will carry a piece of what was once our world. So when you feel small under the night sky, remember that you are part of this grand, quiet story. You are stardust, borrowed for a moment, woven into the fabric of the universe, and destined to drift onward when your time comes. The stars do not hold their gifts for themselves. They share them freely, scattering their riches with every new birth and every quiet death. They teach us that nothing is ever truly lost. Every atom, every element, every memory is part of a cycle that has no true beginning and no final end. A promise written in the light of distant suns that the universe is always becoming, and so are we. You are stardust. When you look in the mirror, you might see your face, your hair, your skin, the small details that make you you. You might see the marks of time, the freckles from summers past, the lines that come with laughter and years. But beneath all of that is a truth that connects you to the entire cosmos. You are stardust. Every part of you, from the air you breathe to the bones that carry you, was once inside a star. It is an idea so vast and so gentle that it can change how you see everything. Long before there was an Earth, before oceans and forests and cities, the universe was a place of clouds and darkness. Giant stars were born in those clouds, fusing hydrogen into helium, helium into carbon, and so on. These stars lived short, brilliant lives, pouring their light into the universe. When they could no longer hold themselves together, they died in spectacular explosions called supernovae, scattering their ashes far and wide. Those ashes were not waste, they were the seeds of everything to come. The iron in your blood that helps carry oxygen through your body was made in the heart of one of these massive stars. So was the calcium in your bones and teeth, the carbon that forms the structure of your cells, the oxygen that fills your lungs with every breath. Even the gold that might circle your finger in a ring or rest against your skin as a necklace was born in the unimaginable heat and pressure of a dying star's final moment. The atoms in your body have traveled across millions of light years and billions of years to find each other here in you. Think of that the next time you feel ordinary. There is nothing ordinary about being made of the same material as distant galaxies. You are a walking, breathing collection of cosmic memories. You carry in you the history of stars that lived and died long before our sun even flickered to life. Those atoms have danced through the birth and death of other worlds. Some may have floated in a cloud of gas for eons before joining the swirl that became Earth. Others may have passed through volcanic eruptions, ancient forests, or the bodies of creatures long extinct. And now, for this brief moment in the universe's story, they are gathered here to make you. It is a humbling thing to know, but it is also a gift. It reminds you that you belong. No matter how small or lost you might feel on some nights, you are made of the same stuff that lights up the night sky. The stars that shine overhead are not strangers, they are family. They are distant cousins whispering that you too are a part of this endless cycle of creation and transformation. And when your time here is done, your stardust will not disappear. It will drift back into the world, carried on the wind, washed away by rain, buried in the earth. Over countless years, those atoms will join new stories: a blade of grass, a bird's feather, a grain of sand on a faraway beach. Maybe they will someday be part of another living being who will look up at the stars and wonder where they came from. And in that way, a piece of you will go on, part of a song that never really ends. This is the stardust cycle. It is the reason the universe feels so familiar, even though it is so vast. Deep down, you know it because it is what you are. Every heartbeat, every breath, every word you speak is stardust, remembering what it can do when given the chance. When you feel the warmth of sunlight on your face, you are feeling the same fusion process that made your elements billions of years ago. When you look at the night sky and see a shooting star, you are watching the same cosmic dance that built you. So tonight, as you lie back and let your thoughts drift like comets through your mind, remember that you are not just in the universe is in you. You are not just looking at starlight. You are made of starlight, shaped by the same forces that sculpted the galaxies. This is your cosmic heritage. It is older than any story told by human lips, deeper than any ocean, brighter than any city's lights. Let that truth settle gently around you, like a blanket of stars. You are stardust, and that means you are part of a story that is far bigger than fear or worry or doubt. A story that began in the dark, in the dust and the fire, that continues every time you breathe, and that will carry on long after you have drifted into dreams. The stars above you shine because they are alive with memory, and so do you. Star clusters, families in space. If you have ever stood in a dark place far from the city lights and looked up, you may have noticed that some parts of the sky sparkle with little knots of stars. They are not just scattered randomly, they gather close together like tiny gatherings of light, nestled in the darkness. These gatherings are called star clusters, cosmic families drifting together through the galaxy, bound by a common birth and the gentle tug of gravity. Most stars, including our own sun, are not born alone. They begin life inside great clouds of gas and dust called nebulae. Within these vast nurseries, pockets of material collapse under their own gravity, forming dozens or hundreds, or even thousands of stars at once. Like siblings born of the same parent, these stars share the same chemical fingerprints. They are born from the same cloud, warmed by the same shock waves, and nurtured by the same swirl of stardust. There are two main kinds of star clusters: open clusters and globular clusters. Open clusters are the younger, more carefree families. They are often found in the spiral arms of galaxies, where fresh clouds of gas keep giving birth to new stars. Open clusters are loose gatherings. Their stars might number in the dozens or the thousands, scattered across just a few light years. When you look at the Pleiades, sometimes called the Seven Sisters, you are seeing an open cluster. Through a telescope, you can see that there are not just 7 stars, but hundreds of faint companions shimmering in that family portrait. Open clusters shine with the bright blue and white light of young stars. They are restless and alive. Over time, though, the gentle push and pull of other stars and the gravity of the galaxy itself begin to pull these families apart. The stars drift away one by one, scattering like siblings who grow up and move to distant towns. Eventually, the cluster is gone, its members now scattered throughout the galactic neighborhood. Our own sun likely began its life in an open cluster 4.5 billion years ago. Its siblings are still out there somewhere, drifting through the Milky Way, carrying pieces of the same stardust that built our solar system. Then there are the globular clusters, the ancient elders of the stellar family tree. Unlike the loose, young, open clusters, globular clusters are dense spheres of stars packed tightly together, like bees swarming around a hive. Each globular cluster can contain hundreds of thousands or even millions of stars, all bound together by their mutual gravity. Some of these clusters orbit far above or below the plane of the galaxy, like glittering lanterns marking the edges of the Milky Way's halo. Globular clusters are ancient. Many of their stars are among the oldest in the universe, born more than 10 billion years ago when the galaxy was still young. They shine with a softer, warmer glow, not the fierce blue of youth, but the steady light of stars that have settled into their long middle and old ages. When you gaze at a globular cluster through a telescope, it is like peering into a memory. You see a snapshot of the early universe, a record of the time when the first great families of stars came together. Inside these clusters, stars live close to one another, dancing in orbits shaped by the combined gravity of their countless neighbors. If you could stand on a planet inside a globular cluster, your night sky would blaze with thousands of brilliant stars, each one so close that they might outshine the moonlight we know on Earth. The stars whisper to each other with their gravity, tugging and shaping each other's paths across eons. Star clusters are not only beautiful, they are clues. They help astronomers understand how galaxies formed and changed. By studying the stars in a cluster, we can learn what the universe was made of billions of years ago, how the first elements spread out, and how the early dance of gravity sculpted the great spiral arms and shining cores we see today. Perhaps most comforting is what star clusters teach us about connection. Even in the vastness of space, stars are rarely alone at birth. They come into the universe surrounded by companions, sharing warmth and gravity and light, and though time may scatter them, their origins remain written in their atoms. Like distant cousins, they carry a shared memory of where they began. So tonight, If you see the soft glow of the Pleiades, or glimpse a photo of a globular cluster sparkling like a jewel box in the sky, remember that you are looking at a cosmic family. Stars, like people, thrive in connection. They are born together, drift together, and carry a piece of each other wherever they go. And in their gentle drifting clusters, they remind us that we too are part of something larger, a family of stardust, scattered yet forever linked by the place where it all began. Stars and the galactic dance. Sometimes, when you stand under a clear night sky far away from city lights, you might catch sight of a wide, soft band of light, stretching from horizon to horizon. This is our Milky Way, not just a distant object, but our own home seen from the inside out. What you are really seeing is the combined glow of billions of stars, each one moving through space as part of an ancient and ongoing dance that has shaped our galaxy for billions of years. The Milky Way is a spiral galaxy, a great wheel of stars, gas, and dark matter spread out like a cosmic pinwheel in space. Our Sun is only one star among perhaps 400 billion others in this vast city of light. Each of these stars, whether young or old, bright or faint, is bound by gravity to the galactic center. And just like planets orbit stars, these stars orbit the core of the Milky Way. At the heart of our galaxy lies something remarkable, a supermassive black hole called Sagittarius A. It is millions of times the mass of our Sun. Although it does not shine like the stars around it, its gravity holds the entire galaxy together, anchoring the stars in their orbits as they circle around its hidden darkness. This invisible heart keeps the dance moving, step after step, through time. Imagine this: our Sun, along with the Earth and the rest of our solar system, is on a journey around the galactic center. We travel at an astonishing speed of about 220 kilometers per second, yet the distances are so vast that it takes the Sun roughly 225 million years to complete a single lap. Since it formed about 4.5 billion years ago, the Sun has made this journey only about 20 times. The last time we were in this galactic neighborhood, dinosaurs were just beginning to roam Earth's forests. The stars near us are dancing too, each with its own unique path. Some stars take longer, wider orbits that swing them far above or below the flat plane of the galaxy. Others trace tighter circles closer to the crowded center, moving through dense swarms of stars and clouds of gas. Together, these countless paths weave the beautiful fabric of the Milky Way, a living, spinning tapestry of starlight. This grand galactic dance is not chaotic, but it is not perfectly orderly either. Spiral arms wind outward from the center, like the arms of a cosmic whirlpool. These arms are not made of fixed stars, but are more like waves, regions of higher density that sweep through the galaxy. As gas clouds and stars move into these arms, the gas compresses, triggering the birth of new stars. Young, bright stars light up the spiral arms, making them visible across vast distances. From our place inside the Milky Way, we see this structure edge on. When you look up at that milky band across the night sky, you are gazing into the plane of our galaxy. You are looking through thousands upon thousands of light years of stars, gas clouds, dust lanes, and hidden dark matter that binds it all together. It is humbling to realize that what appears as a single swath of light is really a vast river of suns, each one traveling its own path, yet moving together in a cosmic pattern older than any mountain or sea on Earth. Sometimes, stars do not stay on their paths forever. Gravity's influence stretches far and wide. Great clouds of dark matter pull on stars from unseen distances. Nearby stars pass close to one another, nudging orbits and sending stars into new courses. Over millions of years, these small tugs add up, shaping the galaxy's structure. Even whole star clusters can be pulled apart and scattered like glowing confetti along their orbits. Yet, for all its shifting complexity, there is a certain peacefulness in knowing that our sun and the stars you see at night are part of this gentle rotation. We are passengers on a grand carousel of starlight, riding along through the spiral arms, circling the quiet heart at the center. When you think about how the sun's orbit carries us through different regions of the galaxy, it is easy to wonder how these journeys have shaped Earth itself. Changes in our galactic environment might have influenced climate, steered comets toward us, or even played a part in life's unfolding story here. So next time you stand beneath the stars, remember that you are not looking at a fixed sky. You are watching a dance that has been twirling since long before humans ever looked up and wondered. Every star is a dancer, every orbit a step, every spiral arm a flowing ribbon of light. The Milky Way is our cosmic ballroom, and whether you can see it faintly overhead or only in pictures, it reminds you that you are part of something vast, something moving, something endlessly beautiful. In this dance, you are never alone. The same stardust that formed you drifts through the arms of the galaxy, pulled by gravity, shaped by ancient forces, woven into the river of light that makes the Milky Way glow against the night. And while the stars swirl and orbit in patterns too slow for our eyes to see in a single lifetime, they carry us all forward together through the dark, brightening the night with their quiet, ageless steps. Cosmic time travelers, Beates pleistud bidig, tikos atequites, bishana fate wef and forsequit than straf. Have you ever stood beneath the night sky and felt, even for a moment, that you were looking into something timeless? There is a reason for that feeling. When you look up at the stars, you are not only seeing light, you are seeing the past. Each tiny dot that twinkles above you is a messenger from another time, carrying with it the memory of when that light first set out on its long journey through the universe to reach your eyes. Light, though it moves faster than anything else we know, still takes time to cross the vast distances of space. Our sun, for example, is about 150 million kilometers away. Its light travels at 300,000 kilometers per second, but it still takes about 8 minutes for sunlight to reach Earth. When you feel the sun's warmth on your face, you are feeling light that left the sun 8 minutes ago. You never see the sun as it is, only as it was just moments before. Now imagine a star much farther away. The light from Alpha Centauri, our closest stellar neighbor, takes over 4 years to get here. When you gaze at Alpha Centauri shining in the dark, you are seeing it as it was 4 years ago. If something happened there right now, if that star suddenly disappeared, it would still shine in our sky for 4 more years before its light finally faded away. The farther you look, the deeper you travel into the past. Some of the faint pinpricks you see in the night sky are thousands of light years away. Their light set out when ancient civilizations were building temples and telling stories about the very stars they saw overhead. Imagine a single beam of starlight leaving its home before humans learned to write, crossing the emptiness of space, undisturbed and unchanged, only to arrive here just in time to touch your eyes. And it does not stop with stars alone. When astronomers peer through powerful telescopes, they can see galaxies so distant that their light has been traveling toward us for millions, even billions of years. Some of the galaxies we observe are so far away that their light began its journey long before our Earth was born. When we see these galaxies, we are seeing them as they were in the distant past. Baby galaxies forming their first stars, colliding, merging, and evolving into the grand spirals and giant ellipticals we see closer to home. In this way, the night sky is a natural time machine. It does not let us visit the past, but it lets the past visit us. Every photon, every tiny particle of light, is like a story that the universe has been waiting to tell. It arrives quietly, carrying with it the secrets of where it came from and what was happening there when it began its journey. Sometimes the light is from a calm, steady star that has burned unchanged for eons. Other times it is the last bright flash of a supernova, the explosive death of a massive star that poured its energy into space for one final moment. There are even lights that come from black holes, or rather from the fierce hot disks of gas that swirl around them, heating up as they are pulled toward the abyss. All of it comes to us, carried on these delicate, patient beams of light. It is almost poetic to think that the starlight we wish upon, the light that guides sailors and inspires poets, is really a message from long ago. When you sit under the stars with your thoughts drifting like comets through your mind, you are not just looking at distant suns, you are surrounded by memories. You are bathed in ancient stories that traveled millions of kilometers every second through clouds of gas, past drifting planets, across the spiral arms of our Milky Way, until they found you here. This is one of the most comforting truths of the cosmos. Light connects us to a time far older than any calendar. The stars remind us that we too are part of time's river, moving forward, carrying within us the echoes of what has come before. Just as you see the stars as they were, someone, somewhere, may one day look back at the light from our sun, drifting through the galaxy long after Earth is gone, and they will see our world frozen in that single beam. So tonight, as you close your eyes and drift into sleep, remember that you are a cosmic time traveler too. Your eyes and mind become a bridge through which the past lives again. Each time you look up, you are not just stargazing, you are time gazing. You are catching the light of ancient fires that still burn in the darkness, reminding you that even when the night feels long, there is always light waiting to find you, no matter how far it has had to come. Take a moment with me now. Let all the facts and cosmic journeys settle like soft stardust on your mind. Let the noise of the day drift away until you feel as if you are floating beneath a wide, endless sky. Picture the stars above you, each one a tiny flame, burning quietly in the dark. Some are young, bursting with blue-white energy that pours into space like a river of light. Others are older, their glow softer, their light more golden, like lanterns that have been flickering for billions of years. It is a peaceful thing to imagine these stars, scattered like seeds across a black velvet field. Each one is a reminder that even the darkness is never truly empty. There is always a spark somewhere, hidden just beyond what we can see, sending out its gift of light to drift through the universe. And because light must travel, we see these stars not as they are now, but as they were. It is as if the night sky holds 1,000 memories all at once, a tapestry of moments woven from the birth and breath of ancient suns. Picture a giant star, swollen and red, reaching the end of its long life. Imagine it exhaling its layers, gas drifting away in gentle clouds that will one day become part of something new. Somewhere else, a massive star burns hot and bright, and when its time comes, it will not go quietly. It will roar into the dark with a supernova's brilliance, scattering its heavy elements like jewels flung into the void. Even its ashes are a promise, seeds for new stars, new planets, maybe even new forms of life. It is all connected, nothing wasted, nothing truly lost. Each star's gift becomes part of the next, and in this quiet moment, you are connected to it too. Inside you is the iron forged in some forgotten star's heart, the calcium and oxygen formed in the heat of a sun that shone before our own. Every breath you take is a reminder that the universe recycles itself endlessly, turning dust into stars, stars into dust, and dust into living beings who look up and wonder. So let yourself wonder now. Picture the clusters, families of stars drifting through space together, bound by gravity and a shared birth. Think of the spiral arms of our Milky Way, sweeping outward like the brushstrokes of a cosmic artist, carrying billions of stars along quiet paths that take millions of years to complete a single circle. Somewhere in that grand wheel is our sun, making its steady way around the galaxy, pulling Earth and the other planets along for the ride. And as it goes, it gathers new dust, sheds old bits of itself, and dances with the faint pull of distant stars doing the same. If you could see it all at once, the galaxies, the clusters, the drifting clouds of gas lit by newborn stars, you would see a universe alive with quiet motion, a universe that burns and breathes but never truly rests. There is something comforting in that, isn't there? To know that no matter what happens here on this tiny world, the stars keep shining, keep aging, keep scattering their gifts into the dark. Their light will drift through space long after our troubles have faded into memory, carrying with it the stories of everything that ever was. Perhaps tonight, when you close your eyes, you will carry this image with you. Imagine yourself lying beneath a sky so clear you can see the Milky Way stretching from one horizon to the other, a soft river of starlight painted across the black. Feel the quiet in your chest as you breathe in that thought that you are part of this, not separate from it. You are made of the same stardust, cradled in the same gravity, carried along in the same cosmic dance. You do not need to understand every detail to feel the truth of it. Sometimes it is enough to look up, to feel the hush of the night, and to remember that somewhere out there, a star is burning just for you. It does not know your name, but its light will find you all the same, brushing your face with a warmth that began its journey before you were born. And someday your stardust will drift outward too, joining the quiet scattering that has been happening since the first stars blinked awake. So let yourself rest now, wrapped in this truth like a blanket made of stars. Let the vastness comfort you. The universe is wide, but in this moment, it holds you close. Sleep gently, stardust, and dream of the light that connects you to everything that ever was, and everything still to come. And now, dear cosmic dreamer, we have come to the end of our starlit voyage. You have drifted through galaxies and nebula, through the birth cries of newborn stars, and the quiet sighs of those that have grown old and gone. You have traced the spiral arms of our Milky Way, and floated in your mind's eye among the glowing clusters that drift like families through the dark. Tonight, you have become a traveler through time itself, catching the ancient light of stars that burned long before we had names for them or for ourselves. Take one last deep breath and feel the stillness that comes when you remember you are part of this grand, quiet story. There is no edge to it, no final page. The universe is always writing itself anew, scattering the gifts of dying stars so they can become seeds for tomorrow's suns, tomorrow's planets, tomorrow's life. And you, resting there in your warm bed, are proof that the stars do not give up their light in vain. You carry their memory in your bones, in your blood, in every breath you draw tonight. Close your eyes for a moment and picture the sky above you. See it not as an empty roof of darkness, but as an ancient map. Each point of light is a word in a language older than any spoken on earth. It says you belong. It says you are never alone. Somewhere out there, even now, a distant star is sending out its gentle glow. One day, perhaps long after you and I are gone, That light will reach another set of eyes, eyes that will wonder, just as we do, how it feels to be made of stardust, drifting through a universe that remembers. Tonight, may you find comfort in knowing that your worries are so small compared to the grand weave of stars and planets and cosmic dust. The burdens you carry will not last forever, but the light within you will. It is a light that once burned in ancient suns, that danced through the arms of the galaxy, that found its way to this little world so it could rest here in you. Even when life feels heavy, that starlight flickers inside you, steady and patient, waiting to remind you who you are. So rest now, starlight. Let your thoughts drift like comets across the vast night sky. Let the swirling galaxies spin gently around you as you dream. Let the cosmic lullaby sing you to sleep, each note a reminder that you are made of all that is ancient and all that is yet to come. The stars above you have seen the birth and death of worlds. They have watched mountains rise and seas dry up. They have witnessed the laughter and tears of countless lives, and still they shine. Still they whisper that it is all connected, all worth it, all beautiful in ways we may never fully understand. If you have felt wonder tonight, if you have felt even a small spark of connection to this great gentle universe, I hope you will carry it with you tomorrow and the day after that. And when the world feels too much, remember that you can always come back here to this quiet corner of the cosmos where curiosity and calm meet under the starlight. Thank you for letting me be your guide tonight. Thank you for drifting through the stars with me, for letting your mind wander through the past and the future, for remembering, even for a moment, that you are more than you know. If you found peace in this journey, I invite you to leave a gentle like on this video. It helps more sleepy minds find their way here to our little corner of the universe. And if you wish to drift again through starlit stories and cosmic dreams, please subscribe and join me next time under the endless sky. Until then, rest well. May your dreams be starlit and your nights filled with the hush of galaxies spinning softly above you. Sleep sweetly, fellow traveler. Good night, starlight. May you always remember that the universe shines through you too.